Okay, hello and welcome everyone to today's invited speaker. Before I introduce our invited speaker, I'd like to take a moment to introduce the Responsible AI program. Responsible AI is a multidisciplinary, multi-sector training initiative to build sustainable connections, research training, and knowledge capacity, and a pipeline of highly qualified trainings in Canada's fastest growing knowledge economy sector, which is artificial intelligence. The Responsible AI initiative is a part of NSERC's collaborative research and training experience, a program known as CREATE. So I have the privilege of introducing Professor Michael Winikoff, who is a full professor with the School of Information Management at Victoria University of Wellington. He's known for his work on engineering aspects of autonomous systems, including the Prometheus methodology. More recently, he has been working on issues relating to trust in autonomous systems, including verification and explanation. He is on the IFAAMAS board of directors, was the program co-chair and general co-chair for the Conference on Autonomous Agents and Multi-Agent Systems in 2012 and 2017, respectively, and is currently co-editor-in-chief of the Journal of Autonomous Agents and Multi-Agent Systems. So thank you very much, Michael, for accepting our invitation and joining us today. The floor is yours.
Thank you very much, Ibrahim. It's a pleasure to be here. Now, I should mention the way that Zoom works, I can see my own screen. I cannot see other people very well, so it feels a bit like talking to a blank black wall. If I was doing this face-to-face, I'd start by asking the question, who in the room has been to New Zealand? And I can't see people's hands or responses. So instead of that, what I thought I'd do is have a couple of slides just to give you a sense of where New Zealand is and a little bit about the country, and then I'll dive into the presentation proper. So as that map suggests, New Zealand is a long way from Canada, although not quite as far as the map might suggest. And New Zealand on this map looks fairly small. That's only because we're sitting next to Australia, which is a lot bigger, which is where I used to be based. If you look at New Zealand superimposed on Europe, you can see that it is actually a reasonably large country in terms of the geography. However, it's not large in terms of population. We have roughly 5 million people, a third of whom live up in Auckland, which is the biggest city. I live down in Wellington in the middle there, which is the capital of New Zealand. And these days, New Zealand's perhaps best known as the setting for the movies, The Lord of the Rings. And in those movies, the hobbits, Sam and Frodo, have to travel a very long way to get from their home in the Shire, Hobbiton, to Mount Doom to destroy the One Ring. And in New Zealand, where these places were shot, those two places are actually not far apart. They're about 200 kilometers. So Mount Doom is actually just a mountain that was used as a backdrop. Hobbiton is a tourist destination these days. It's the set that was used to shoot all the outdoor scenes. And it's literally a sort of large paddock with recreations and lots of round doors. It's well worth a visit. So that's a little bit about New Zealand. Now, I understand that the people here today are quite diverse in terms of their backgrounds, so computing, engineering, sociology, and possibly others as well. So what I thought would be useful is to start off by just defining a few terms so that at least we're on the same page in terms of what different terms mean and what different concepts are. So obviously the one that gets mentioned a lot is artificial intelligence, or AI, and there are a lot of misperceptions and misunderstandings about AI in the sort of media, mass media. And I think the main point I would stress is that it's a discipline, a very broad one, that looks broadly at a whole bunch of techniques for how do we get computers to display intelligent behavior, which usually or almost invariably is sort of narrow. So it's intelligent behavior in one particular type of problem. So AI includes sub areas such as planning, representing and reasoning with knowledge, robotics, speech recognition, processing images, processing natural language. And then within AI, there's one particular sub area, machine learning. And within that, one of the approaches used is neural networks. And then deep learning sits under that as a particular type of neural network. So that's the sort of big high level view of artificial intelligence. Autonomous systems, which is the other term that I use, an autonomous system is a system that can act in a way that has real-world consequences. And as you can see in the diagram down the bottom, there's significant overlap between autonomous systems and intelligent systems, but they are distinct things. So an example of a system that might be intelligent but not autonomous is something that perhaps learns and then based on what it's learned from data gives advice. So maybe it recommends to a human whether to accept a certain deal or not. An example of an autonomous system that is not intelligent is something like an extreme example would be a thermostat. It makes decisions, it has real-world consequences, but it's not using any sort of AI techniques. And of course, there's overlap in the middle. So various autonomous systems, whether they're robots, self-driving vehicles, smart personal assistants, often do use some techniques from the field of artificial intelligence and including techniques from machine learning as well. Now, the focus of my talk is on explanations, and I should probably say a little bit about why explanations are so important. I'm mindful that I'm probably preaching to the choir in a lot of cases here. So an explanation is just information that explains why a particular decision was made or a course of action was taken. And explanations from systems are important for a number of reasons. One of them is trust. So if a system does something and we're not quite sure that it's doing the right thing, providing information on why it did that might help us to develop and maintain an appropriate level of trust. And the word appropriate is important. If a system is performing badly, then the appropriate level of trust is actually a low one. And having more transparency, having explanations might help us realize that the system is not doing a great job and that we should not trust it that much. Explanations are also important for accountability. So if a system does something and something goes wrong, then we need to understand how the system reached its decision in order to work out where the issue was and who to then try and hold accountable. Similarly, if we're going to try and contest or challenge a decision of a system, so perhaps the bank came back and said your loan application was declined, our system told us that we should decline it. If I want to contest that decision, it really helps if I understand on what basis the system recommended that my loan application be declined. And finally, transparency and explanation are important when we're working together with systems. So this is more the sort of human agent team setting. So if you're working in collaboration, say with robots, then having an understanding of what the robot is doing, how it's about to try and do it, can really help with the coordination. Now, this idea that explanations are important is not a new one. So I've got a quote there from a 1981 paper. This was in the context of an expert system providing advice to medical practitioners. And what they found was that the ability of a system to explain its advice was actually not just the most important attribute to the physicians, but it was more important than the ability of the system to understand and update its knowledge base. And it was more important than the system being necessarily giving always correct advice. The quote down the bottom there is a much more recent one from a white paper from the White House that was published earlier this month, that automated systems should provide explanations. Now, that's a white paper. It's not in any way legally binding. So these are some of the reasons why explanations are important. And I'd like to highlight that these explanations are especially important when a software system does something that's not obvious, or it finds a solution that's not an obvious one. So a simple example there is if you're driving along and normally your navigation system takes you on a particular path, but today it takes you on a different path. So it's useful if the system says, hey, I'm doing this for a reason, there's congestion on the normal path. The other point that's worth highlighting here is that the way that computer systems exhibit intelligent behavior in a given domain is often very different from the way that humans operate in that domain. So an analogy there is that a plane and a bird both fly, but they fly in very different ways. And just to illustrate that, I've got a few examples here. So imagine that I gave you photos and asked you to identify baseballs. You would be looking for small round objects and maybe then looking for patterning. The images up the top are from a paper a few years ago where they trained a system to recognize certain images. And each of those 4 images are ones where the system would come back and say, I'm really confident that, say, that third one along is a baseball. So this is highlighting that when a system learns to do things like recognize images, it does not necessarily do it in a way that's at all similar to how we as humans might do that. And that's important to understand, because if they're doing things differently, there may be places where they are vulnerable or brittle. And that second example illustrates that. So there's no way that a human would misinterpret that second sign as a speed limit, but that was carefully engineered in an adversarial way. So the system that was recognizing signs there was misreading that. And the last term that I use, and that's actually the title of the talk, is explainable agency. And what I'm highlighting there is the difference between explaining machine learning systems, which a recent paper sort of termed as data-driven explainable artificial intelligence, and explaining autonomous systems, which has been termed goal-driven XAI, or in a slightly older paper, explainable agency. And in fact, most of the work within the field of explainable artificial intelligence focuses on machine learning. So my work focuses on the sort of smaller, less worked area of autonomous systems. So that's the sort of background and concepts and terminology. And today I'm going to look at 2 questions, and I've changed the order there from the abstract because of being a diverse audience, I thought I'd tackle the one that's probably more of a sort of broader interest first. And that is, how can we motivate organizations to deploy explanation mechanisms? And then I'll come back to the question of how do we get autonomous systems to explain themselves in an effective way. So that first question was considered in a paper that Julia and I wrote a few years ago. Julia is my wife, in the interest of full disclosure. And the key question we considered was, suppose that we do have good explainable AI techniques. How can we then encourage organizations to use them? So for example, imagine a bank. The bank has a system that maybe it's bought and deployed or maybe developed that recommends whether to approve or decline loan applications. So the bank may actually prefer not to provide explanations. They may prefer to be a little bit more opaque in how the decisions are made. They might feel that if they're too transparent, then people might feel empowered to challenge their decisions, or that they might, if they're too transparent, it might become visible that what they're doing is in fact problematic in some way. Or it just may be that developing and deploying these systems takes time and money, and they're not particularly keen to have to invest that. So how can we encourage, or maybe incentivize, or even require organizations to provide mechanisms for explanations from their intelligence systems? And of course, one answer to that is, well, we can lobby and eventually perhaps legislate and have new laws. And the issue with that is that, of course, it takes time. So the question we considered was, can we have an argument that says, look, there is an obligation on organizations to provide these explanations, and can we base this argument on existing obligations, legal obligations? And one set of existing obligations is human rights. So this is not my area. I should have probably mentioned my background is as a computer scientist. My wife's background is in sociology, so it's more her area. And one reason why human rights are an interesting thing to look at in this context is that there is a Universal Declaration of Human Rights, which came out in the UN in the aftermath of World War II. And there's a subsequent, the ICCPR, which is the sort of legally binding embodiment of that. And that's been adopted by a long list of countries. So you can see the map there. It's not universal, but it sort of does cover certainly a large number of countries, and significantly more than, say, if you look at the EU. As an aside, the GDPR, which is legislation with the European Union, mentions explanations, but in fact that comes in non-binding recital. The actual binding part just says some meaningful information about the logic. So it does not appear that that creates an obligation to provide explanations of any specific decision. So if I apply for a loan, the bank might say, well, the system was given broadly this information, and here's a sort of 2-page that talks about what sorts of things the system was given, but not sort of any information about why my particular case was declined. So what we did is we looked at the Universal Declaration of Human Rights and went through with a intelligent system and explainable AI lens. So we were considering to what extent would deploying intelligent systems affect different human rights, and to what extent we're focusing on where would explanation be something that might naturally arise as something that would be required to avoid those human rights being violated. So the basic scenario is, imagine that some organization is subsequently taken to court and there's a case saying, look, I have human rights in the country where this occurs, there is some legally binding version of those. And based on that, my human rights are being violated because the organization is doing something with intelligent systems, say a bank deciding whether to provide access, and it's doing it in a way that's not transparent. So maybe there's a possibility of discrimination happening. So I won't go through this figure in detail. What we found and highlighted were 2 particular areas where we felt that there was a case for saying, look, based on human rights, consequently, there is an implied requirement to provide explanations in certain contexts. So the first one relates to discrimination. So there are a number of human rights that relate to the right to access certain things, social security, standard of living, higher education being equally accessible. And in determining access to all of these things, there is another criteria that says that another requirement that says that various criteria such as race, color, and so on cannot be used. And one of the issues that does arise with intelligent systems is that they can be biased. Now, we sometimes see the argument, well, hang on, how can a computer system be, for example, racist? And the answer is that computer systems can be racist, and they can be racist or discriminate on other bases, even if they've not been programmed to do so, because if they're learning from data, and the data that they're using often does have within it embodiments and reflections of historical biases, then what the machines will learn is to reproduce some of those biases. So a simple example that illustrates this is translation. So I don't know if we have any Hungarian speakers in the audience. This is text in Hungarian, and I chose Hungarian there because it's gender neutral. So that at the start of each is the sort of they are, effectively. So they are beautiful, they're clever, read, and so on. And if I ran that a while back through Google Translate, I got the following. So the original Hungarian doesn't say he or she, it just basically says gender neutral they. And what Google is doing there, or was doing there, was basing its translations on what it was seeing in the wild. So if you go searching, you will find a lot more occurrences of she is beautiful than you would he is beautiful. So reading that, it's reproducing gender biases that exist in the text that can be found out on the web. And of course, all these biases are problematic. It's problematic that this is effectively assuming that politicians are male, that people baking cakes are female, that professors are male, and that assistants are female. So this is just one example of discrimination that can arise from machine learning because of the underlying data. Now, to give Google a little bit of credit, if you try and translate one of those phrases, then it does come back and say, actually, the translation is gender specific and it could go either way. And when I reran that translation yesterday, I got a slightly different version that is slightly different in the gender. So yes, we still have she being beautiful, but we have he being an assistant and he being a cleaner, for example. And it does also have a disclaimer up the top saying, look, some of these sentences might be gender specific. So discrimination is an issue. Discrimination where it occurs is a violation of human rights if it's based on prohibited criteria. So one in a lot of cases, problems have simple solutions that don't work. And in this case, a simple solution that does not work is just to say, okay, fine, if we're not allowed to discriminate on gender, we just won't tell the system about gender. We won't tell the system about ethnicity. And the issue there is that systems that are learning systems, one of the things that they do, that they're meant to do, is to find patterns in data. So for example, if you are applying, learning whether to approve or decline loans, and in reality, there is a strong pattern historically of certain groups being more likely to be declined, then a good machine learning system will sort of try to find that pattern, even if it's not given the key variable, if there are other variables that can function as proxies. So an example there is in the US, say ethnicity, is correlated with postcode. So if I say, right, my loan system, I won't tell it the ethnicity of the people applying, but I'll give them the postcode, then it may learn that certain postcodes, it should be declining. And then when somebody comes back and does an analysis, they'll realize, oh, in fact, what we're ending up doing is disproportionately declining certain ethnicities. And the system doesn't see ethnicities, but it's being able to learn that through the proxy of postcode. And there are a whole bunch of other proxies that could be used. So for example, a human resource system might look at the patterns of employment. And again, if there are certain breaks in employment or people living part-time, that in our society tends to correlate with being female, for example. So the argument here is that explanation is crucial to detect and ideally avoid these sorts of discriminations. Without explanation, it's difficult to know whether a particular application was declined because of a reasonable criteria or an unreasonable criteria. So that's one area. The second area that we flagged was judicial applications. And as you might expect in a human rights document, legal rights are quite prominent. And that's also because legal processes have significant outcomes that can affect a lot of human rights. So for example, depriving someone of their physical freedom by sending them to jail, impinging privacy in various ways, depriving someone of property ownership, even citizenship removal. So a lot of these things are significant consequences that are very much bound up in human rights, and they're affected in a lot of cases by legal processes. And there are also rights that relate to the process of the legal system. So again, not having discrimination, but also having things like a fair hearing and the right to be informed clearly of the charges that are being placed against someone. And the word arbitrary appears a number of times, and that's also significant. So if a judicial process has an outcome, then that cannot be arbitrary. And again, to avoid discrimination, to ensure that the tribunal is independent, to be informed, and to avoid arbitrariness, explanations are really important for that. We also talked about a couple of other ones. So just fairly quickly, there's a right to freedom of opinion and freedom of expression. And if we imagine the social media scenario where everything that we post, everything that we see is curated by an algorithm, then our right to share our opinions with others, our right to access other people's expressions of opinion is being mediated through a system and perhaps is being distorted in certain ways. And some ways may be, as we've grown to learn over the last few years, quite unhealthy for us as individuals or indeed for our societies as functioning democracies. Health, again, to the extent that health is provided or health research is done using underlying data and machine learning, there are a whole range of issues that come up again in terms of discrimination. So historically, a lot of health research has been done on subgroups of the population, and that has caused issues where the findings may not exactly generalize perfectly to other groups. So that's a sort of short answer to how can we motivate organizations to deploy explanation mechanisms without requiring new laws. And there appear to be a number of cases where the right to get an explanation can be argued to be a consequence of the existing human rights obligations that exist. The second question was, okay, so we've convinced organizations to develop and deploy explanation mechanisms. How can we get an autonomous system to explain itself effectively? So this is joint work that I did a few years ago with Galina, Virginia, and Frank. And again, we have a paper with a married couple. Frank and Virginia are married. And the key argument that we adopt is that in order for an explanation to be effective, that is effective, comprehensible, understandable to humans, one approach to do that is to use the same concepts that we naturally use in our own explanations. So if you come to me and ask me, why did I do a certain action? Then there's a lot of research in social psychology that says, look, humans in these situations for these particular types of things, so an autonomous entity that's intentional, that's following a course of action, we tend to explain those using three concepts. So in particular, our work leans heavily on this book. And the three concepts are beliefs, desires, and valuings. So an example would be, why did I buy coffee from the shop? And the answer might be, well, I believe that I have money, so I have the ability to do that. And I value the quality of coffee that I get from the shop. And I had a desire to perhaps get this particular coffee or just get coffee in general. So that's an argument for, well, if you want to explain autonomous systems effectively, maybe we should try using these concepts, beliefs, desires, and valuing, because that's what we as humans use. And within the field of autonomous agents, there are various approaches for how we engineer, design, and build autonomous systems. And one approach that's quite widely used and well developed is what's called the belief, desire, intention architecture. So those of you who are familiar with object-oriented programming, the idea there is that programs are developed in terms of the concept of objects and perhaps classes and inheritance. So it's a metaphor for how you structure software. In this case, an autonomous system is developed using software constructs that are analogous to beliefs, goals, and in fact plans that correspond to those things. So in writing software, you write the beliefs, you write the goals, you write out plans. And as you might guess there's actually a nice close analogy that if you develop software using this idea of beliefs and goals and plans, or that following the BDI architecture, then it actually turns out to be fairly natural to then pull out of it explanations that use beliefs and desires. So one of the things that we then had to do was extend the representation with something for valuings. So at a high level, this is the sort of picture. So a human asks a question, which might be, why did you do this particular action, or why did you do this course of action? And the system provides an explanation. And it develops that explanation using some sort of process from its own internal representations. So in developing an explanation scheme for explainable agency, there are basically four key questions we have to ask and answer. What sorts of questions can be asked? So for example, a simple one might be, why did you do this? There are also other questions that could be asked. Why did you believe something at a certain point in time? Why did you not do something? Why did you do this instead of that? What forms can answers take? And we've argued based on the social psychology evidence that sort of phrasing them in terms of beliefs, desires, and valuings is a good way to go, and that's understandable to humans. And then how do we actually get these answers from the questions? What internal representation do we use? And then what process do we use to take a question, take the internal representation, and work out what the answer should be to that question? So the contribution of the paper, other than sort of highlighting that analogy between belief, desires, valuings, and belief, desire, intention architectures, is to answer those last two questions. What internal representation do we use? And then how do we derive answers from that internal representation? So the framework that we use, the internal representation, is basically a tree of nodes. So a tree here means it's in the sort of graph sense, where you can think of it as a diagram where each box is a node and it has children, in this case, on the right. Each node represents something that the system is trying to do or achieve, and its children represent sort of how do you do that. So it's being decomposed with more detail. We have three types of decomposition. So in some cases, For example, if I want to get coffee from the kitchen, then I have to do all of the children underneath that. And in fact, I have to do them in a prescribed sequence. I need to get a staff card, go to the kitchen, and then get the coffee from the kitchen. Some nodes have alternatives. So if I want to get a staff card, I can do that by getting my own card or by asking a colleague for theirs. And when we have alternatives, we sometimes have conditions as well. So if I want to get coffee from the kitchen, then I must have my staff card with me, otherwise I can't do that. So this sort of formulation, a tree of goals and actions, is a fairly standard one in the autonomous systems literature. And we've specifically said, look, you want to have pre and post conditions, and we add to that a representation for valuings. The way that we do that is for certain nodes, we attach an indication of the outcomes of that course of action. So if I get coffee from the kitchen, then the key aspects that I care about here are the quality of the coffee, the cost, and how far do I have to go. And the kitchen coffee is not great quality, it's free, and there might be a certain distance. And we also capture preferences over these different valuings. So I've mentioned pre and post conditions, that's the sort of preferences, the valuings there. So I'll use a running example, which is getting coffee. It's inspired by a real scenario when I was visiting Virginia and Netherlands. And the basic scenarios there is I would like to get a cup of coffee, and there's 3 options available. I can go down the hall and get coffee from the vending machine in the kitchen, which is free if you have a staff card, and it's not great quality, but it is free. I can go to my colleague and get a coffee from her office, and there's a coffee machine in there that uses pods, and of course she has to be in her office for that to be possible. Or if I have money, I can go and get really great coffee from the coffee shop. So if we have this internal representation, and there's a particular course of action that was taken, and the question is asked, why did you do this? Why did you get coffee from the shop? How can we derive an answer to that question from this representation? So the high-level intuition is that you can imagine a branching tree. So a timeline where what actually happened went from T0 to T1 and so on, and eventually we led to an action A. But at each point, there may be an alternative that could have happened. So all the things that explain why we didn't take those other alternatives are part of the explanation for why we ended up doing the action A that we got to. So that's a sort of high-level intuition that we started at the beginning. We could have made other choices, and at each point when there was a choice, the thing that led us on our present path is part of the explanation. And if we apply that to that representation, then there are a number of different cases, and this is just to give you a bit of a flavor. The details, of course, are in the paper. So when we do an action, part of the explanation is that that action could be done. So if I buy coffee, then part of the explanation is that I was able to do that, so I had money. And all of the bits of the tree that sort of lead to that and play a role have to be included. So for example, if there were other actions along the way, then they also had to be performable. And the interesting case turns out to be, perhaps unsurprisingly, where choices are made. So for an or decomposed node, so that's where there's something and there are different options for how we could do it, we include the condition of the selected option. So the particular option that I selected, the thing that made that be able to be selected. If there were other options that I could have otherwise selected, but in fact I couldn't, then the reason why I could not do those is also part of the explanation. So for example, if one option was going to my colleague's office, but in fact she wasn't there, then that's part of the explanation. Why did I get coffee from the shop? Because I couldn't get it from my colleague's office because she wasn't there. And then if there are other options that in fact were available and I chose not to select those, then there's an explanation in terms of preference. So for example, here, if I got coffee from the shop, then that first case corresponds to, well, because I could, because I had money to do so. An example of that second case would be, well, I was getting coffee from my colleague's office was not an option because she wasn't there. And that third case example there would be, well, I could have also gotten coffee from the kitchen and I chose not to do that because I prefer the good quality coffee. So these cases, and there are a few other ones beside that I won't go into now, were all formalized and defined precisely in the paper. And then we went on to implement the reasoning. So given the representation, given a question, there are algorithms that will pull out an explanation. And we showed that these algorithms are efficient. And there's also templates. This is not sort of full-on natural language processing. It's sort of taking patterns and rendering them into English. And there's a few examples there. So that I got coffee from the shop because it has the best quality of coffee, and that happens to be the most important attribute. Or I chose to get it from the kitchen with a poorer quality of coffee, despite quality of coffee being more important because it was cheaper and closer. And we showed that these algorithms are efficient, both empirically and analytically. But coming back to the opening claim, we are arguing that this approach of providing explanations in terms of desires, beliefs, and valuings is understandable. So to test that claim, we did evaluations. In fact, we had 2 human participants evaluations. Both of them were surveys where participants were given scenarios, different explanations, and asked to rank them. And there are some examples of the explanations there, and the explanations included these different factors. So there were examples of beliefs, there were examples of desires, of valuings, and in fact in this one there was also an example of another factor where you would do something in order to be able to do something else later. And what we found is that these explanations are indeed understandable, and that the valuings were actually seen as being the sort of most valued aspect of the explanation. So given a choice between different explanations, people were more likely to select explanations that included valuings than they were to select ones that, say, had beliefs or desires. So to summarize, explanations are important for a whole range of reasons around understanding how systems operate, coordinating with them, being able to challenge them. And that's especially the case because intelligent systems don't function like humans. So the plane versus bird analogy, and we saw examples of that. And we saw that we can motivate a legal need for or legal obligation to deploy explanation by leaning on existing human rights obligations. And their approach then that I presented for how autonomous systems can explain themselves effectively is to use the same concepts that we use: beliefs, desires, and valuings. And I briefly presented the formal framework, the internal representation that we use for that, and the mechanism where we take that representation and then derive explanations. And that was implemented and evaluated. So a few years ago, when I sort of started talking about some of these topics, I'd sort of finished my talk with this slide. With the rise of self-driving vehicles, there will eventually be a country song about how your truck left you too. And when I was preparing for this talk, I did a search and actually realized that this slide is now wrong, because I was able to find 2 examples of country songs that are about how a self-driving truck left someone. So by the way, I'm happy to share the slides if anyone's interested. So thank you very much for your attention. Very happy to take questions, and I'll stop sharing now so I can see the chat and see people.
Thank you very much, Michael. Very interesting talk, and a very interesting ending there. What we typically do is we stop recording at this point before we go into the QA. I hope that's